Chapter 4. Exterior Products and the Cartan Method. General relativity analysis usually requires computation of the Riemann tensor for the spacetime of interest. The most economical way to do this is by use of exterior products and the Cartan method, aka Cartan calculus. For point 1 derivation of the Cartan calculus. Beginning with the conventional definition of exterior derivative, we add 1. D produces a p plus 1 from d sigma from a p-form sigma. 2. D times alpha wedge alpha equals d alpha wedge d alpha plus negative 1 to the p times alpha wedge alpha and d squared equals 0. 3. df equals gradient sub af with gradient sub of the covariant derivative. The exterior, antisymmetric differentiation of tensors is defined by equation 4-1, where
equation 4-2, where alpha is a p-form and beta is a q-form. We extend the definition to exterior derivative on exterior product of tensor-valued p-form S with ordinary q-form beta, thus equation 4-3. So if see the equations, then equation 4-4. Now, let's apply the formalism.
See the equations. So, dE sub mu to the a and w sub b to the mu plus e sub mu to the a dw sub b to the mu equals 0. Here e sub mu to the a is a vector-valued 0 form. Equation 4-5.
Let d times e sub mu sub b to the a equals e sub v to the a times w sub mu to the v sub b I e d sub mu equals e sub v w sub mu to the v in less explicit notation, where w sub mu to the v is a 1 form. Since gradient sub beta e sub alpha equals e sub mu gamma sub alpha beta to the mu, we find that w sub mu to the v sub b equals gamma sub mu gamma to the v times w to the gamma sub b. Thus w sub mu to the v equals gamma sub mu lambda to the mu w to the lambda dash. Now, consider v to the a equals e sub mu to the a times v to the mu. Let's take dv to the a dash colon.
dv equals e sub mu times dv to the mu plus w sub v to the mu v to the mu implies d squared v follows. Equation 4-6. Now the exterior derivative for a 1 form contracted on a bivector u wedge u. Equation 4-7. Generalizing to a tensor-valued 1 form. Equation 4-8. So, 4s equals dw a vector-valued 1 form. Equation 4-9.
Note that the general p-form is a completely antisymmetric tensor of rank the 2 by 1 column matrix 0p. Equation 4-10. Where the vertical bars denote summation only over I sub 1 is less than I sub 2 is less than ... is less than I sub p. Example, suppose you have U is a vector-valued 0 form, vector, sigma bar is a scalar-valued 1 form, Then, equation 4-11. Cartan differential forms, 1928, 1946 Leçons sur la géométrie des sphères de Riemann, then start by considering equation 4-12. For which
equation 4-13. Let's now write the differential of the typical vector-valued 1 form e sub mu as d sub mu equals e sub v omega sub mu to the v. There the components omega sub mu to the v in the expansion of d sub mu are 1 forms. Furthermore, note that omega sub mu to the v equals gamma sub mu lambda to the new omega to the lambda dash. So, the expansion of the vector-valued 1 form is equation 4-14. Similarly,
equation 4-15. Now, equation 4-16 generalizes to equation 4-17. So, equation 4-18. Thus, the 2 by 1 column matrix 1-1 tensor value 2 form are evaluated on the bivector parallelogram u wedge u is identical with curvature operator r prime of u v above.
Equation 4-19. So, equation 4-20. Thus, equation 4-21 provides packaging of 21 curvature components into 6 curvature 2 forms. The gamma sub alpha beta to the mu goes to our sub v alpha beta to the mu calculation becomes omega sub v to the mu goes to our sub v to the mu calculation. The g sub mu nu goes to gamma sub alpha beta to the mu calculation becomes a g sub mu nu goes to omega sub v to the mu calculation.
The g sub mu nu goes to omega sub v to the mu calculation proceeds from two features. 1. The symmetry of the covariant derivatives. 2. And its compatibility with the metric. Condition 1. Appears hidden in d squared p equals 0 times wh of e of r e of left angle bracket dp, v right angle bracket equals v, i.e. dp is a special form of the generic the 2 by 1 column matrix 1 1 tensor t equals e sub mu t sub v to the mu omega to the v with t sub v to the mu equals delta sub v to the mu dash colon. Equation 4-22. Putting this in.
See the following group of equations. We get equation 4-23. Note that gradient is said to be symmetric, torsion-free, when see the following group of equations. So, d squared p equals 0 demands the symmetry of the covariant derivative and vice versa. Equation 4-24. Consider 2 can be expressed as
equation 4-26. Let u equals e sub mu wedge e sub mu equals e sub v. Equation 4-27. Then, equation 4-28. Returning to the expression left angle bracket d squared omega, u wedge u right angle bracket equals gradient sub v omega minus gradient sub u omega minus gradient sub u v omega equals r of u v omega. Equation 4-29.
Let's consider evaluation of the Riemann tensor from the Cartan forms. Now R of u, v, above is the curvature operator which is related to Riemann by equation 4-30. So, in our notation, equation 4-31. Recall. See the equations. Thus, equation 4-32. Now compatibility of covariant derivative with the metric means.
Equation 4-33. Thus, for an orthonormal frame, d of g sub ab equals 0. Let u equals e sub mu, v equals e sub v. Equation 4-34. Synopsis of computation of curvature using exterior differential forms. Symmetry of covariant differentiation, i.e. torsion-free.
Equation 4-36. Consider a tensor valued one form S of any rank. It satisfies. Equation 4-37. If S equals dw, a vector valued one form, then using left angle bracket dw, u right angle bracket equals gradient sub uw we get. Equation 4-38. Where script r sub v to the mu equals r sub v times the absolute value of proportional to beta to the mu w to the proportional to and w to the beta dash. Now consider S equals e sub mu w to the mu equals dp in Cartan's notation.
Equation 4-39. Compatibility. Equation 4-40. For an orthonormal frame dg sub mu v equals 0 and w sub mu v equals negative w sub v mu, leaving only 6w sub mu v to solve for in 4 dimensions. Script r sub v to the mu equals dw sub v to the mu plus w sub alpha to the mu and w sub v to the alpha dash.
For point 2 Riemann tensor for 2-sphere, let's use Cartan calculus to write down the independent components of the Riemann tensor in an orthonormal frame for the 2-sphere with metric. Equation 4-41. And find the Ricci scalar. Solution. We have. See the equations. Where. See the following group of equations. For. See the equations. We have. See the following group of equations. Thus.
See the equations. Thus. See the following group of equations. Thus. See the equations. And we get. See the following group of equations. Thus. See the equations. And the rest 0. The Ricci scalar is. See the following group of equations.
4.3 Riemann tensor for 3-sphere. Let's use the Cartan calculus to write down the independent components of the Riemann tensor in an orthonormal frame for the 3-sphere with metric. Equation 4-42. And verify that. See the following group of equations. Solution. We have. See the equations. Thus. See the following group of equations. Using.
See the equations. These choices are consistent. See the following group of equations. Using. See the equations. We get. See the following group of equations. So. See the equations. Follows from above then. See the following group of equations. Gives. See the equations.